right, everybody. Thank you for attending. I want to welcome our speaker today, Dr. Andy Getz, who's an associate research scientist at the San Diego Supercomputing Center and founding faculty member of the newly formed SYCL School of Data Science and Computing. Andy leads a research group in data-driven and high-performance computational chemistry, where they focus on quantum mechanics, molecular dynamics, and machine learning approaches to enable molecular simulations on massively parallel computer architectures. He's a developer of the GPU accelerated quantum chemistry software called QUIC and contributes to the AMBER project, a widely used biomolecular simulation package. And he's also co-founder of the Atmos Incorporated company, which develops technologies for computational drug discovery, and his work in HPC architecture and scalability has contributed to the deployment of supercomputers such as SDSC's Cosmos system. He's authored over 80 publications, edited the book titled Electronic Structure Calculations on Graphic Processing Units, and his research has been supported by the NSF, the NIH, the DOE, Intel, Nvidia, and AMD. We welcome Andy today and thank him for offering to present this talk today. Andy, you are in charge.
Okay, thank you very much for the nice introduction, Mary. Let me share my screen. Okay, can everybody hear me okay? And can you see the screen?
Oops. Yes.
Okay, great. Let me try to switch on the laser pointer. Okay. Somehow the laser pointer is not coming on. Yeah, that should be here. Okay, that's better. All right. Yeah, welcome everybody. So this is a little bit of a different webinar from many of the others where we have some introductions to our supercomputers and advanced computing concepts, programming, and similar. So this is an overview of the history and the hardware in terms of GPUs, how we can program them, just a very brief overview, and then how we used GPUs to enable larger and faster simulations in molecular dynamics, density functional theory, and QMMM simulations. And sorry, there's something in the way here. Yeah. So just as a background, so the San Diego Supercomputer Center has over 40 years of history. I like to start with this history because it's nice to see how hardware has developed over that time. It was established in 1985 as a national supercomputer resource by the US National Science Foundation. And then in 1997, integrated with the University of California system. And since 2024, we have the Hartree School of Data Science and Computing that Mary mentioned with the two departments, the Supercomputer Center and the Data Science Institute. And at SDSC, we are about 250 people with on about 100 researchers doing excited work. And so this is, both buildings still exist, they're connected. So this is the original building, and this was the building, the new building that we have since 2009. And over that time, supercomputing has changed quite a bit. So the first supercomputer that we had at SDSC was a Cray XMP in 1985. In terms of performance, it had 800 megaflops out of 4 vector CPUs. And if you fast forward, our current production system, national production system, SDSC expands, has about 5.2 petaflops in terms of high performance computing capability. And that comes from CPUs, from AMD, and from GPUs. So we have NVIDIA V100 GPUs. It's about 6 million times faster. And just fast forward 5 years, this is a current testbed system that we have at SDSC. It's a Cray system again. So we went from Cray back to Cray, although it's not really the same company anymore. But the name, of course, is still there. And it's 15 times smaller, but gives us twice the performance. So, I mean, we still have massive improvements. And we'll see where all of this comes from. It comes a lot from specialization. And so one thing that I like to tell people is that, future HPC systems probably will be customized in one way or another, and we're seeing this already with lots of specialized hardware, different types of accelerators for different types of applications or compute workloads. And today we'll focus on GPUs, but there are many other types of accelerators, and computational scientists need to develop algorithms and software so that we can make use of that hardware most efficiently. Where does this trend in GPUs come from, and so why we're are we talking about massive parallelism and so on? And so this goes back to how transistors have shrunk, and how we can build better and faster hardware. And so many of you will be familiar with Moore's law that says that the transistor count in integrated circuits doubles about every 2 years. And so this exponential growth still holds. So these are these yellow dots here. So you can see the transistors in a processor, microprocessor, still exponentially increasing. But what changed since about the mid 2000s here is that the clock frequency stayed about constant. So a single CPU core is not much faster. So the performance increase is mostly due to an increased number of logical cores per processor. And you can see that, now we have these multi-core processors that have already on the order of tens to even going into the hundreds of cores per CPU. So for software, that means you cannot wait 2 years to double your code execution performance. You have to write parallel code. And what do GPUs have to do with any of that? And so GPUs, so these are old plots, so it would be nice to have an update, but I don't have a great update, but it gives you a little bit of an idea what is the difference between GPUs and CPUs, and in particular in terms of the computational capability in terms of floating point performance, but also memory bandwidth. And you can see that the FP64 floating point performance of at least data center GPUs has been always significantly higher than CPUs, but also important the memory bandwidth. So GPUs typically have memory with a high memory bandwidth. And that's also very important because many algorithms, or probably the majority of algorithms nowadays, is actually memory bandwidth bound. And this whole development was driven by, really big gaming industry. And now it's just really the AI industry exponentially growing, much bigger than the gaming industry even. And if you compare that to the NSF and the NIH budget, you can see that, as scientists, we basically have to take the hardware that we can get. It's not built specifically for the applications that we need to run, but we need to make the best out of it. GPUs are good at data parallel computations, matrix algebra, and of course, over the last years in particular, because there are many matrix operations in AI workloads, well suited for deep learning and AI workloads. So, just as historically putting this together, basically you could say you have a supercomputer in a desktop. So ASCII Byte was the fastest supercomputer there's this list, it's called Top 500 in the world, at least the open, academically accessible or known to the world. So 12 teraflops. And if you compare that, your teraflop, in Expanse, we have a 3.4 petaflop performance. And if you go to a box that you can put together yourself, you can buy, this example is a picture that I had in the past in older slides. There were still 4 GPUs, and it's harder to stick 4 GPUs into a self-built system, at least if they are consumer GPUs, but you can stick 2 in easily. And with that, 2 RTX 5090 GPUs from Nvidia, you reach 3.2 teraflops in FP64 performance. So that's already a good fraction of the performance that you had on the ASCII Byte supercomputer, or over 200 teraflops in 32-bit floating point operations. And that is a cost of 10,000. So everybody has now really, really a lot of compute power at your fingertips. We have Expanse. I don't want to talk much about Expanse because this talk is not specifically about Expanse, but This is our main supercomputer at STSC, National Compute Resource. And we have 52 GPU nodes on it with a total of 208 GPUs. There is a new partition that has, I don't know exactly how many, but a very large number of H100 more modern, more powerful GPUs for AI applications. So those are allocated differently and they are specifically meant for AI applications. So I'm not mentioning these here much. And if you look at this, we have our compute nodes, and then there's 4 GPU nodes in each of those racks. And then there is many, many racks for a total of 208 V100 GPUs. And, it's a standard supercomputer connected to I/O nodes for doing I/O operations, to fast parallel file system, and login nodes to submit the jobs to the different queues and so on. But if you look at the specific compute nodes, they look something like this. This one here is not exactly an expanse GPU node, but the GPU nodes, they have basically CPUs. In this case, we have 220-core Intel Xeon Gold CPUs on each node. If you look at this, so there's a CPU here and a CPU here with the coolers on top. And then there are 4 of these Nvidia V100 SXM2 GPUs. And those are GPUs that literally go onto the motherboard, into this SXM2 sockets. And this is what you can see here in this example in the front. So there's like 4 of those GPUs, and these are the coolers. And here are the fans that are pushing the air through the system. So in Expanse, we actually, the GPU nodes are still air-cooled. And each of those GPUs has a good amount of memory, 32 gigabyte. It's not a lot compared to what you can get nowadays, and it's certainly much less than you can get as RAM on CPUs. But depending on the application, that's more than enough. And then there's node local NVMe storage, and all of those 3 GPUs, they are connected by very fast interconnects, so which is of advantage if you have a simulation in which you use multiple GPUs. A little bit different is Cosmos, and I want to mention it briefly because this is our newest systems, and it has also GPUs. It's completely liquid cooled. There was a slide earlier where you've seen something, so this is actually a picture of Cosmos. And it's just a single rack that gives us a lot of performance because each one of those compute blades, so it's very dense. They don't need much space because they don't have air cooling. Everything is liquid cooled. So if you look at this, these are the liquid cooled blades, compute blades, and the blue connectors basically have the cooling liquid come in, and then the red is the warm liquid comes out. And here at the bottom, this whole part of the rack is actually a cooling distribution unit that cools the liquid by a heat exchange with water that is supplied for cooling the system. So it is much more efficient and nice because it keeps cool and it keeps quiet, and is also more power efficient. But what's interesting is each of those compute nodes has 4 so each blade has 2 nodes, and each of those nodes has 4 AMD MI300A accelerators. So those are basically chips that have, they're called APUs, accelerated processing units, and they have both a GPU and a CPU on the same chip. I'll show it on the next slide, and more memory available. And then this is just a total system configuration. Similar to what you've seen on Expanse, we have like 4 of these processors, and they have these very fast interconnects. Now, the difference is there's no additional CPU processors because the CPU is inside of these processors. And let me show you on the next slide. So that's where you can see this is one of those processors. And so there's this HBM3. This is this very high bandwidth memory. It's here on the side on the chip. And this one is the processor. And there are these vector and matrix GPU cores in one of these chiplets, which AMD calls accelerated compute dies. But besides the accelerated compute dies with a GPU cores, there's also three that have each 8-core Zen 4 CPUs. So there's basically here a total of 24 CPU cores. And then we have here quite a large amount of GPU processing power, all on a single chip. And this design is interesting because all of these, both the CPU and the GPU portion, have access to the same memory, so you don't need to move data between the RAM of the CPUs and the RAM of the GPUs, which can make applications and in particular software development more efficient. So that's what we have at SDSC, but also overall, how does the HPC environment for scientific computing look like, and why have we been so interested in GPUs over many years now? And it's literally because many of the systems nowadays almost all systems are heterogeneous. And the most powerful ones are heterogeneous computing system, meaning that we have both commodity CPUs and GPU accelerators that give the majority actually of the compute performance. And then all of this is in the compute nodes is interconnected with special interconnects, and you have to do basically programming that's highly parallel with a distributed memory system and MPI or MPI plus OpenMP programming models. And they're all a little bit different. Like, El Capitan has AMD-based system with APUs. Its architecture's practically identical to Cosmos, only Cosmos is much smaller, of course. These are the DOE, the largest computers that we have in the US. Aurora is Intel-based. So it has both Intel CPUs and Intel GPUs, and they work a little bit different. We have to program them differently. And then this again is an AMD-based system. Like I said, at SDSC, we have a mix of AMD and Intel CPUs and then Nvidia GPUs. And finally, there's a very special supercomputer also that we have, which is called Voyager, that you can't run regular applications on it because it has special AI processors. So that's really only for AI applications. Over the years, this is interesting to show. It goes back to the slides that I showed you with Moore's law. We still have these performance improvements, and over time, so teraflop was achieved in ASCII red machine, the first machine that crossed the teraflop. Petaflop, that was in 2008, the fastest supercomputer. Again, national lab, of course. And you can see that took about 11 years to get these 3 orders of magnitude of improvement in terms of peak performance. And then it took another 14 years to get to exaflops. And now everything is starting to become different because, with all the AI processes, we don't necessarily do 64-bit floating point operations anymore and so on. But one take-home message is, these 3 orders of magnitude has become harder because, we've shrunk so far in terms of the features on the chips on the nanometer scale that it's really hard to build something that is faster and more efficient. And so it's hard to develop these things, but it's also hard to program them. And this is another slide that I took from Jack Dongara. It shows instead of what you saw on the slide before is the peak performance in terms of a LinPack, which is a linear algebra benchmark, which is not representative of what most applications actually do. Instead, most applications do something that's more close or similar in terms of like algorithm and memory access patterns to conjugate gradient application benchmark. And that's much harder to implement and to scale and to get performance out of it. And so here the ranking is according to the HPCG performance. And you see the fastest supercomputer, this is for 2022, but similar, looks still pretty similar, was not the one that has the highest HP LinPack performance. And the second thing that you can see is that the HPCG performance is much lower. It's not 1000, it's not 1 exaflop, it's 14 petaflops. And so what that means is that the real applications really only get a fraction of the peak performance. So in terms of floating point performance of what those machines can do, because a lot of the algorithms go into, memory transactions and moving data between the processors. And so the fastest supercomputers, we get with GPUs are hard to program. It's not that trivial. You can get good performance out of them, but it's hard to get peak performance. So you'll get maybe a 1%. That's like, yeah, it's basically like driving in a Ferrari, but you are constrained by having a speed limit of 10 miles per hour. So how do GPUs look like? Just a very, very, very broad and simple overview, and how can we program them? So if you look at a GPU and compare it to CPU, schematically, so on a CPU, and you think about, how much space you have in terms of like real estate on the processor on the chip. On a CPU, we have fewer processing cores, but they have much more sophisticated hardware that does things like multi-level caching, branch prediction, prefetching, and so there's more control units and cache. And then you also have access to a larger RAM. GPUs on the other side, they have many more, so thousands, it's literally thousands of more simplistic compute cores. Those are packaged typically into multiprocessors. Differently, you could say you have also on the orders of tens of processors, but each of those processors has many processing units that operate in lockstep. So you have to make sure that all your operations happen at the same time. And you do things like vectorized loads and stores to memory, and you also have a little bit more exposed memory hierarchy that you have to manage to some extent, or at least think about where the data is sitting, so you get good performance. And this is very old, 2009. So this was the first Nvidia GPU architecture for data centers. So the Tesla T10, a server with a C1060 data center GPU. The reason I put it on is because the basic architecture is not different. Of course, there's lots of technological advances and changes, but you have these multiprocessors that I talked about. So you look at this, so you have several processors. I don't remember exactly how many processors we had. You could make the count from here. But there's multiple of these, what NVIDIA likes to call symmetric multiprocessors, or SMs. And each of those processors here has several compute cores. And in this case, FP32 single precision compute cores, then a double precision compute cores, typically less of those special function units, instruction cache, and so on. And then something that's called shared memory, which is basically a data cache. The thing is, it can handle many more, and it could back then already, threads than processing cores. So you can actually launch more threads. And that's one of the things that is different from CPUs, where typically you write a multi-threaded program and you want to have one thread per CPU core. On GPUs, that's different because you can actually have multiple active threads on one of these multiprocessors. If your kernels, so the functions that run the GPU code, are not too complex. And that can hide memory latency, because while some threads are doing some compute, the other threads are basically waiting for data, and then everything gets switched out automatically, and the runtime handles that for you. As opposed to in the past, one thing that is different nowadays is tensor cores. So all the modern GPUs have tensor cores. And this is specialized hardware for deep learning in particular that helps to accelerate matrix multiply and accumulate operations. So where you have something like a matrix multiplication here between two matrices A and B, and plus matrix C, and you can store that and you get the result back. And so these are operations that are often used in deep learning neural networks, fully connected or linear or dense layers, convolutional layers, recurrent layers, and similar. And because these deep learning applications can get away with lower precision, in particular after the neural networks have been trained, there have been different data types that have been introduced, right? So there's like, Nvidia Volta was the first GPU that introduced tensor cores with FP16 data types. And FP16, obviously, for scientific applications is typically not sufficient to maintain precision that is required for accurate results. But then there's like support for FP64, TensorFloat, 32, bfloat, BrainFloat data types, and so on. And now we are at FP8 and maybe, I don't remember, FP4 data types operations. The one thing to keep in mind is that though for scientific applications, tensor cores can also be exploited. And in particular, that often works very well if you have some linear algebra that you can express in terms of these tensor operations. The one thing you have to be careful with is precision. Okay, so this is again, you've seen on the Tesla T10, this is now a streaming multiprocessor on a V100. This is basically just a diagram that shows you how that looks like. So the GPU, that's the V100s that we have on Expanse. The GPU has 32 gigabyte of RAM. And then it has 80 of these streaming multiprocessors. And each of those streaming multiprocessors has 64 compute cores basically to do FP32 operations. So if you'd count them, you'd find like 16 here times 4 is 64. And then there are 32 FP64 cores. And then there are some tensor cores, and that gives you this sort of like performance per GPU or peak performance theoretical. So about 8 FP64 teraflops. And so how do you program these things? So there are multiple ways to do that. And it depends on your applications. It also depends on the type of GPU. So most prominently known probably is CUDA, which is NVIDIA's proprietary framework for programming and the whole software stack that they have. And it's a de facto standard for many high performance codes, both in scientific applications and machine learning and AI. Then we have HIP, which is similar to CUDA. It's an open source C++ runtime API and kernel language that was developed by AMD. It literally looks almost like CUDA and was certainly inspired by CUDA. And it works both with Nvidia GPUs and AMD GPUs, where it compiles basically with a CUDA backend or AMD's ROCm, which is the equivalent of the CUDA software stack. So these are probably the most widely used frameworks to program GPUs for high-performance computing. There's also OpenCL, which is an industry standard, and it works across NVIDIA, AMD, and Intel GPUs and many other devices. It's just a little bit more low-level, harder to program, and not as widely used for scientific applications as CUDA or HIP. Something that's actually came out of OpenCL is also by the same, the Kronos group, developed as a standard is SYCL, which is, again, is also a single source, high-level standard C++ programming model. And that can target a range of heterogeneous platforms as well, CPUs, GPUs, and FPGAs in principle. But of course, again, if you develop code with SYCL, at the end of the day, you still have to write it in such a way that it runs, good on the hardware you want to run on. So that's always the case, performance portability. So even if you had a compiler for SYCL that compiles for different hardware, or if you had something like that for CUDA or HIP, you still need to adjust your algorithms and the source code so that the data structures and the algorithms that you implement map well to the underlying hardware. It's very hard to do this automatic, so that's called performance portability. So even if the code is portable, that it runs on different hardware, it's not necessarily efficient on all of the hardware. So it's even if you have a portable language, it's not always useful. But it's nice to have. And of course, if you want to program Intel GPUs, that's the only way to do it at the moment, like with SYCL. Or the other thing is there's OpenACC and OpenMP. So those are accelerator directives. So OpenACC for NVIDIA, in particular, in principle, NVIDIA and AMD, but to my knowledge, there's no good compiler for AMD, and so you're stuck with NVIDIA. Works with C++ and Fortran. So if you have compiled language codes. The other one is OpenMP. So version 4. I don't remember which one, but since version 4, basically there's accelerator and vectorization directives with a target offload to GPUs. And so this is becoming mature and it actually works quite well. I have a colleague who's been using this quite successfully on Cosmos, for instance, and also across different hardware. And of course, that then will work on also on different GPUs, AMD or NVIDIA GPUs or Intel GPUs. The downside is usually performance is best if you write dedicated kernels in CUDA or HIP for the target architectures or SYCL if it's Intel GPUs. And so what you do in heterogeneous computing is, you have what we call a host and a device. So host is basically the CPU code, and it's your standard C, C++, or Fortran code. And then you have the device, which is basically running this parallel code, kernels that we call kernels that are executing on the GPU. And then again, you have a serial portion of the code. And you could think about it, you move data from the CPU to the GPU. You do a matrix multiplication and you get the results back on the CPU, and then you do something else with it. And you think about it, so you have the CPU with its own memory, and then it's connected to the GPU, which we call device, via typically PCI Express bus or some other fast interconnect. And then what you do is you copy your input data from the CPU memory to the GPU memory. Or if you have a system like Cosmos where the memory is the same, you don't have to do that. Then you load the GPU program. So you launch the kernels that you wrote, execute it, and then you copy the data back. And so I talked about kernels. What is a kernel? A kernel is a source code that you wrote. So here an example here on the right, there's a kernel for addition. It's called add1 is the name of the function. It's a function basically that executes on the GPU. And what happens is the kernel operates in lockstep on the multiprocessors or compute units of the GPUs in so-called warps or wavefronts. And so that's just language that's used by NVIDIA and AMD. And sometimes it's 32, or AMD has sometimes 64 threads in one of these wavefronts. And it's also typically called SIMT, so single instruction executed by multiple threads. And what is a thread? A thread is an execution unit of a kernel with a given index. So each thread basically knows which thread it is. So each thread knows I'm thread 0 or thread 1 or thread 2 and so on. And so this way you can use a thread and its index to access a subset of the data to operate on. And so this is how you achieve parallelization. So, in a CPU code, if you were to do something like a vector operation, where so you have an array operation, you have an array A and B. So what you do is basically the array A, so you're adding 3 times B to array A. And so you'd have a loop over that. And so the GPU kernel doesn't have a loop. Well, you just launch it with a certain number of blocks. Well, it's called blocks and threads. And then each thread knows, well, I'm thread 0, so I do the addition of the element 0. I'm thread 1, I do the addition of element 1. And of course, you have to have some logic in there to allow to do this for general size and so on. But that's the very basic on how you program GPUs. And these threads are grouped into what is called blocks. And the reason for that is that a block is guaranteed to execute on the same streaming multiprocessor or compute unit. That's how AMD calls it. So on one of these processors that has typically 32 or 64 compute cores. And that means they are running on the same processor, so they can actually exchange and synchronize data. And so you can use that in your program. And then there's the so-called grid of blocks of threads. That's just all threads that are running, basically. I'll have this on the next slide. So you have this kernel, you write these kernels, and this declaration specifier global just means that the kernel can be called from the CPU code. There's also device kernels that you can call from other kernels. So you could think that you have a could have a function call in here for code that executes only in GPU. And so on the CPU code, when you reach a certain part, you have prepared your data, you could launch the kernel with this launch configuration and tell it, okay, execute this now on the GPU with a certain number of threads and number of threads blocks. And so how this looks like, what we just looked at, okay, we didn't look at A equals B plus C. So we looked at A, so add 3 times B to A, but imagine this would have been A equals B plus C. You know, you'd have basically thread 0 might look at, we'll look at elements 0. And so if you have B0 equals 5 and C0 equals 3, then you get a result of 8. And so thread 0 would do that computation. Thread 1 would be doing that computation. And while running on the same block, this happens on the same processor. And then there's multiple warps. So if I say, you know, I told you the warp size is 32 on Nvidia GPUs. If I have, for instance, 64 threads in my block, then I have 2 warps, active warps running. And then I have multiple blocks, and the blocks get distributed across different multiprocessors, and you can have multiple blocks per processor running. And how many threads and blocks you have in your grid, so the total number of threads that you've launched, that depends on the hardware, and you know, you can tune that on the hardware and the kernel that you're running. And you know, the kernels also, launches are asynchronous, so once you launch the kernel, you can continue on your CPU. Another thing that, you know, you have to do is you have to avoid thread divergence. So because in a warp, all these threads, they have to do, the processor cannot do anything else but the same instruction at the same time. So if you have an if statement and thread 1 is supposed to do something else than thread 0, the code gets serialized and that gets executed one after another. So these are the sort of things that you have to be careful when you program GPUs. And then there's memory hierarchy that you have to take into account. You know, the host memory is connected. That's basically by the CPU memory. And then you have what we call global memory. That is the memory that's accessible to all the threads on the GPU. So that is the GPU memory, the GPU RAM. And so that data transfer typically is slow. So you want to avoid that. And then also the global memory, which is visible to all of the threads that are running. So imagine you have a block here that has 2 threads running, another block that has 2 threads running. And so each of those threads can access global memory, but it's slow. There's this shared memory that sits on the processor that's much faster. So, you know, you can use that basically for cache blocking, and it's a fast on-chip memory that you often have to use. You have to be careful to avoid bank conflicts and use padding if necessary, but you know, those are some considerations to take into account when programming for GPUs. And then, yeah, local memory, that's just, you know, if you use too many registers, that spills out of register space. That's not a good idea. So you have to try to write kernels that are small enough so that you don't occupy more memory space while the kernel is running than registers that are available. You can do it, but then, you know, that data gets cached basically in global memory that can become very slow. And then there's additional memory that's called constant memory that has special memory access patterns that you can also use to improve performance. So that's kind of all that I wanted to say. About, you know, how do you program GPUs, and then now I'll give a little bit of an overview of the software that we developed over the time. And just going back, so it's most of the work that I do is related to biomolecular modeling, and I like to show this very nice image. It's from a 2021 paper from Tamar Schlick and collaborators that shows a little bit, how developments in the field have actually always happened in conjunction with the hardware developments. And so, starting was very, very closely with some technology triggers like, parallel computers, and in particular supercomputers. People got very excited. So you're suddenly able to do simulations and that you were not able to even think about before. And then, you become typically, there's a trough of disillusionment because you're like, okay, we can do the simulations, but it's nowhere close to the timescales and length scales that we need to connect to make real predictions about the science that we are actually observing. And then there were many interesting new developments, in particular with GPUs, have really accelerated that. People got quite excited about molecular dynamics with this again. There are special purpose computers have been developed. We had the Nobel Prizes. There was also in 2009, we had the Nobel Prize at, no, when was it? In 98, we had density functional theory. Then 2013 Nobel Prize in Chemistry for basically multi-scale simulations. And now there's so many developments besides QMM, machine learning, quantum computing is coming up. Extending this now, 2024, all the AI developments with the Nobel Prize in Chemistry for Hassabis, Jumper and Baker for protein design and protein structure prediction, and Hopfield and Hinton for, their foundational developments in machine learning with artificial neural networks. There's lots of exciting work now also in AI that, of course, builds on some of those tools that we've been developed and extends those with machine learning interatomic potentials and similar things. And now let me talk about Amber. So Amber is the software that I've been developing for many years, or contributing to. So of course, many developers. And it's both the name of a set of force field parameters for proteins, DNA, other molecules, biomolecules. And for general organic molecules, there's the GAF force field, ions, and so on. But also the name of the simulation package that's been around for over 35 years. Should be maybe 40 now. I'd have to look at it. Many contributors to the code, and it comes in two parts. There's this completely free and open source Amber tools that has all the preparatory and analysis programs, some MD programs. And then there's Amber, which has the high performance MD program, which has an academic license. So it's also free for academic and nonprofit research. And that has the high performance MD code that has the GPU implementation. It's widely used for biomolecular simulations, things like proteins, DNA, RNA, you name it. Gives us basically helps us understand how life works at the nanoscale and biomolecular function and disease and computational drug design. And so the use has grown quite over the years. I don't have newer data here because it's always difficult to say you have a new release and then take some time until people are starting to download and use the new release, etc. But use has grown quite a bit over the years. And that paper, for instance, from 2013, where we published the PME implementation of molecular dynamics on classical molecular dynamics and Amber on GPUs has, on average, and it's been increasing over time, actually, 290 citations per year. So that's actually quite nice to see how widely the code is used. And so as a background, when we model molecular interactions, we can do it with quantum mechanics, or we can do it in other ways. So of course, quantum mechanics, Schrödinger equation or density functional theory is in principle accurate, but it's complicated and very expensive. So we either have to use simple physics-based approximations, or we use this, to do QM training data for AI models nowadays, besides using it directly in simulations. And so if we're not using quantum mechanics at the other end or spectrum of when still doing atomistic models, the most simplistic form is to use a molecular mechanics force field that has, bonded terms, basically ball and spring model, and then harmonic terms for angles, and then, truncated Fourier expansion for the torsions, torsion angles, and some electrostatic interactions between point charges. And this is just a Lennard-Jones potential that mimics dispersion and Pauli repulsion at short distances. So it's a very simplistic representation that works astonishingly well. And with that, you can do something like running molecular dynamics simulations of hundreds of thousands of atoms. For instance, this was a simulation that I did many years ago of the cytochrome C oxidase protein or enzyme. And so there's a reaction center here. So it's the final electron acceptor in the electron transport chain in cells. And water is being produced. And so with the simulations, we basically found out how the water is transported out of the protein. And thing to keep in mind is when we're looking at these things, what are the relevant timescales and what are the timescales that we're looking at when we're running simulations? So what's really interesting is somewhere on the micro millisecond timescales, the time steps that we take in molecular dynamics are on the order of femtoseconds. And that is because otherwise, we can't keep the numerical integration algorithm stable. But what that means is we need to have hundreds of millions of time steps. And if we want to finish any simulation in a reasonable amount of time, we need less than 1 millisecond of wall clock time per time step. So we need to be really fast. And these are older benchmarks, but it shows you why GPUs have been used so widely for molecular dynamics simulations, classical molecular dynamics simulations. If you program these things, the algorithms properly and optimize them for GPUs, you can get very good performance from from consumer hardware to data center GPUs. So that's a V100. It gives you a performance of 50 nanoseconds in the life of a molecule per day. So in 24 hours wall clock time waiting for it, versus what back then was, fastest 36 CPU core CPU nodes, so significantly faster. So that was very successful. When you do that, you also have to pay attention. You cannot simply use just, say, single precision. So the FP32 compute cores, we tried this initially, but then, the simulations drift and blow up. So this is the energy of the simulation with time, and it needs to be stable to conserve Newton's laws. So we have mixed precision implementations where we do most of the compute in FP32, but then we do some accumulation and fixed precision. So you have to be careful with these things. But carefully tuning the codes and thinking about your algorithms, you can do that. Some of the things that I worked recently on, and I'll skip over this very quickly. I just wanted to show it. We've also been working on porting Amber to SYCL so we can run on Intel GPUs. And if we look later at the slides, it's a performance comparison. So Intel still has decent consumer hardware or professional hardware that is on the lower end, but cheaper price point, has nice comparison actually to Nvidia GPUs. And so it's nice to get the code running on that. It's quite complicated to do. In principle, it sounds easy. You have a program that helps you translate the code. Well, maybe it's easier nowadays when you start, you have coding agents that can help and make that more efficient. And then you basically take the CUDA code, compile it, translate it, fix all the things that the automatic translation couldn't do. And that, this was actually a multi-year project with Intel software engineers. And then you debug and profile and optimize for Intel GPUs. There are many, many source code lines and kernels on the orders of, 500, 450 CUDA kernels, 280 device functions. So very challenging. And then you start somewhere, the first version of the code that works, and then you have multiple trials and tune and optimize different things until you get the performance we got it up to 52%. So on half, that just has to do with how these Intel GPUs are built. There's basically 2 GPUs on one chip. So half of that chip gives you about half of the performance of an H100, which is pretty good. And then additional optimizations where we realize, okay, you cannot just automatically use the full GPU. You have to tune that with MPI, communicate between the different you did it 2 slices of the GPU and got it up to 80% of a H100, which is a pretty nice performance. And so that's what is shown here, the performance on the Intel data center GPU versus the H100 versus some of the other data center GPUs and the consumer hardware, which is actually this very cheap GPU, gives us decent performance. So hopefully that will come out very soon. So I see that we don't have a lot of time left. So I wanted to talk quite a bit about QUIC, but I think I have to go a little bit faster through it. So what I will do is I will show you, mention briefly what QUIC is. It is a quantum chemistry code. And then so I cannot go into the details, but we'll show you some of the performance that we have nowadays. And if you have specific questions about it, maybe I can try to answer those. But it is a Gaussian-based quantum chemistry code that is open source. You can get it here for free. It is also distributed via Amber tools. So it's integrated with Amber tools for doing QMM and molecular dynamics simulations using the Sander MD code. So the classical part runs on the CPU because that's much cheaper than the quantum part, and the QM calculation runs on the GPU. And we can do Hartree, Fock and DFT calculations with Gaussian basis sets up to F functions. It's MPI parallel, works on CPU, but also on GPUs, both AMD and Nvidia. Everything is running on the GPUs. The electron repulsion integrals in particular, and the exchange correlation quadrature and all the linear algebra. And then it's integrated with Amber for QMM and D simulations. So target is basically, you can use it for high throughput QM calculations to say, generate QM training data for AI applications, or reaction profiles and free energies with Amber for QMM applications for computational drug design or enzyme design. And, these are the different components in density functional theory. I don't have exact exchange on there, but we, of course, do have that implemented. But really, for the Coulomb interactions, you need to compute these very complicated exchange electron repulsion integrals, and there are so many of them, and that's really expensive. And the exchange correlation quadrature, which has these complicated functional forms that we cannot solve analytically, so we do it numerically, a numerical integration. And that is also expensive. And so these are the main things, that have been implemented, and there's a range of papers here that describes that implementation. And I will spare you the details now, but I will walk you very briefly through the slides that I have, and feel free to reach out to me if you have questions about that. A brief description of the ERI engine, where we have a code generator to generate the most complex parts of the code for us. This is a brief explanation on how we actually implement the computation of the electron repulsion integrals on the GPU, at least on a high level, with pre-screening to sort them according to types and size, so that we can neglect integrals that are small. That's pretty standard, but that sorting is also important so that the same types of integrals are computed by threads in the same warp. So we don't get this thread divergence that I was talking about earlier. And then this is how we distribute basically the types of integrals across GPUs so that we get good load balancing if we have multiple GPUs in the system. And this is how we implemented the exchange correlation quadrature, where we take the numerical integration grid points and distribute them into batches of grid points that are spatially local again, so that we avoid thread divergence, so that each of the batches of grid points has the same type of work to do. And with all of that, this is just a scaling across multiple GPUs that we can achieve with the code. So if there's sufficient work, if the molecule is large enough, we can get quite good scaling across multiple GPUs. This is the performance that we get on a range of different GPUs, just a benchmark. You can see that, takes about less than 2 minutes to compute an energy and a gradient for a fairly big molecule with 168 atoms and about 1,600 basis functions. But works also well on gaming GPUs. So there's different types of generations of GPUs, both data center and consumer hardware. This was something that we implemented recently, which is electrostatic potential computation, that is significantly more efficient on GPUs than on CPUs, CPU cores. Also, of course, CPU portion is also parallel implemented, but it's really fast to do on GPUs, so that enables very fast automatic generation of electrostatic potentials. And I'm almost done here. This is the QMMM implementation that we have. It's just schematically, it shows you the equations, how they are solved basically by the QM and the MM code, and where we coupled Quick to MM package, in this case Amber, but in principle could be hooked up to other codes as well. So that's done by an API, so Quick used as a library. And with that, you get a little bit of idea about the performance of the code, how many picoseconds per day in terms of simulation we can get for QMMM simulations with about 50 atoms or 160 atoms with 2 different types of basis sets. So it's on the order of 1 to 10 picoseconds per day. And you can see that over the time, we had an improvement both by tuning the code and, of course, adjusting it and adapting it for new generations of the hardware. With that, I'm actually done. I'm at the end. Yeah, thanks for listening. The world of scientific computing is changing rapidly with different types of processors, driven by advances in AI and machine learning. And, we just have embraced this new world, I think. And then I talked about Amber and Quick, our open source multi-GPU capable quantum chemistry code. You can get it from here. And, you can also have Amber tools download for free, and you can get Amber from this website. And with that, you have a fast mixed QM/MM capable code. And there's a few slides with acknowledgement of many of the collaborators who have collaborated both on the science codes, the code development, and also the supercomputers that we use and that fund both running simulations and some of the software developments and optimizations. And with that, thank you for listening, and please feel free to contact me if you have any questions.